Hello everyone, I am Aleena Paul, currently pursuing my Master of Computer Applications at Marian College Kuttikkanam Autonomous. I am excited to be here today to talk about an important topic in software development, code dependency analysis using graph theory. This concept plays a crucial role in managing and optimizing software projects, and I look forward to sharing insights on how it helps improve code structure, maintainability, and performance. So, let's get started. Before we dive into core dependencies, let's quickly understand graph theory. It's a mathematical way of modeling relationships between objects. Imagine each component in your software as a node and their interactions as edges connecting them. Graphs can be of different types: directed, undirected, weighted, or unweighted graphs, each serving different purposes in software modeling. So, what exactly is code dependency analysis? It is the process of understanding how different components of a software system depend on each other. Why do we need this? Well, imagine working on a large project where one change causes unexpected issues in multiple places. With the dependency analysis, we can visualize these relationships, identify circular dependencies, and make better refactoring decisions. In large scale software applications, understanding dependencies is absolutely crucial because it helps in maintenance, refactoring, and debugging. Imagine working on a huge code base without a clear understanding of how different modules are connected. Even a small change can cause unexpected issues elsewhere. This is where directed acyclic graphs come in. Think of each node in the graph as a module or function and the edges as the relationships between them. Basically, which part of the code depends on what? Since it's a directed and acyclic graph, there are no cycles, meaning dependencies follow a clear flow without looping back on themselves. So, what are the benefits of using this approach? First, it helps us visualize the dependencies flow in our project, making it easier to understand. Second, we can identify critical paths. And finally, it ensures that any changes in one module don't negatively impact others, reducing risks in development. In short, it provides a structured way to manage dependencies, leading to more stable and maintainable software. And that's why they are widely used in code dependency analysis. Now, let's see, why does this matter in software development? Well, modern applications are complex with hundreds or thousands of interconnected modules. By using graphs, we can model these relationships, analyze how different parts of the code interact, and optimize workflows. This helps in detecting bottlenecks, understanding module dependencies, and making informed decisions about software architecture. To represent these dependencies, we typically uses a directed acyclic graphs. Here's how it works. Each node represents a file, class, function, or a module, and each edge represents a dependency like an import statement or a function call. Directed acyclic graphs are particularly useful because they prevent cycles, ensuring a clear flow of dependencies. Now that we understand how dependencies are modeled, let's look at some real world applications. Code refactoring. Dependency graphs helps identify tightly coupled modules and simplify complex dependencies. Impact analysis. If we modify one module, how does it affect others? A graph helps us see that. Error detection. Circular dependencies can be problematic, and this analysis helps us catch them early. Optimization. We can optimize module loading and improve execution order based on dependencies. To analyze dependencies, we use various tools. Some popular ones include static analysis tools like SonarCube and PyReverse, and dynamic analysis tools like Graphis. It can be used for visualization and language specific tools. These tools automate the process, making it easier for developers to spot issues. So let's take a real world example. Suppose we have a Python project where modules import each other. By creating a dependency graph, we can identify unnecessary imports. It helps in detecting circular dependencies before they cause runtime errors. By analyzing critical paths, we can prevent cascading failures in the system. This makes our software more robust and easier to maintain. By using dependency analysis, we can improve modularity, detect circular dependencies, and ensure smooth refactoring. This not only enhances code maintainability but also reduces the risk of unexpected failures in large scale applications. Developers, we should integrate dependency analysis into our workflows, leverage tools like SonarCube and Graphs, and ensure our project remains scalable and maintainable. Think about this. If you could instantly visualize the dependencies in your current project, how many hidden issues do you think you have to uncover? That's it from my side. Thank you for your time.